Hi. So we're going to do a couple of examples related to number 14 through 16 on homework 2 that will hopefully help you make sense of those if you're having some trouble. So here we're going to again look at DNA packing, but in actually a different way than what we did in class. So here what we're going to think about is the volume occupied by DNA in different sorts of places. So we're going to figure out the volume of a piece of DNA and the volume of various containers that it may be in, and compare the two. So let's work through an example, or kind of two examples. So first of all, how can we think about the volume of DNA? Well, we know it's a double helix, but we're going to approximate that by just thinking about DNA as a long, that's not a very good drawing, thin rectangular box. Now, for the dimensions of this box, we remember that the width of DNA is about a nanometer. And here, let's go ahead and use the more exact number of 2 nanometers. So that's the width and as well as the height. And then the length of the DNA will depend on how many base pairs, how many nucleotides there are in it. So in our first example here, we're going to think about the human genome. So we're going to think about the human genome. So let me draw out my little box for that. And so here we can ask ourselves, what is the volume of this box? So like we said, the length and width are each, the width and height are each 2 nanometers, which is 2 times 10 to the minus 9 meters. And the length, what is the length? Well, we've stated this in class, but let's think through it again. Our length of that long rod, we have 3 times 10 to the 9th base pairs. And as I write in the problem, each base pair is 1/3 of a nanometer in size. We have 1/3 of a nanometer per base pair and 3 billion base pairs. And so that's 3 times 10 to the 9th base pairs times 1/3 times 10 to the minus 9, because nano means 10 to the minus 9, giving us 3 times 1/3, so 1, times 10 to the 9 times 10 to the minus 9, so 1 times 10 to the 0, or 1 meter. Okay. Good. So the length of one copy of the human genome is 1 meter. Now, the overall length here, well, let's go ahead and think about now the volume. So the volume of our box, or the volume of the human genome, we have, as we've said, in each of our cells, or the majority of our cells, 2 copies. So we have 2 times this length times width times height of our box. So that's 2 times our 1 meter times 2 nanometers. So 2 times 10 to the minus 9, or that's the width of our box, times 2 nanometers, the height of our box. So 2 times 10 to the minus 9 meters. So putting those together, we have 2 times 2 times 2, 8, times 10 to the minus 9, 10 to the minus 18 cubic meters. That's the volume of DNA in each of our cell nuclei. Okay, now what's the volume of the nucleus that the DNA is in. Well, in the homework problem, we approximate the nucleus as a sphere. Let's first do a slightly different example just for variety's sake. Let's imagine that our cell nucleus is kind of like a box that is, let's say, just to pick a number, let's say 6 microns on a side. So what would this volume be? Well, we would have length times width times height for our box, which is 6 times 10 to the minus 6 cubed, which is 6 times 6 times 6 times 10 to the minus 6 times 10 to the minus 6 times 10 to the minus 6. We have 3 minus 6s, so 10 to the minus 18. Sorry, I forgot to write meters. 10 to the minus 18 cubic meters. And we can multiply that out. Hold on just a moment, let me erase this. So the volume of the nucleus, if we imagine it to be a box, would be 6 times 6 times 6, so 216 times 10 to the minus 18 cubic meters. So here, with this little picture of our DNA inside a nucleus that we're thinking of as a box, this volume is like 8 times 10 to the minus 18 cubic meters. This volume is 216 times, sorry, let me rewrite that, 216 times 10 to the minus 18 cubic meters. So our DNA, there's a little DNA in there, takes up a fraction, so this volume fraction is the volume taken up by the DNA over the volume of our container, which is 8 times 10 to the minus 18 over 216 times 10 to the minus 18. These parts cancel out, giving us 8 divided by 216, which you can do that on a calculator if you like, or you can do it kind of approximately. Anyway, however you do it, it's about 0.04, so volume fraction of 0.04 or 4%. So about 4% of the volume is taken up with DNA. Okay. Now, in the actual example that I wrote out on the homework, again, we're thinking of the volume of the whole human genome. So that's 2 copies, each of which are 1 meter by 2 nanometers by 2 nanometers, giving us 8 times 10 to the minus 18 cubic meters. But for our container, our nucleus, being a little bit more realistic and calling that roughly a sphere of radius 3 microns. So the volume of a sphere is 4/3 pi times the radius cubed. So we have 4/3 times pi times 3 times 10 to the minus 6 meters. Good. Now we can, actually let me just keep going here. So that's 4/3 times pi times 3 times 10 to the minus 6 cubed. So we have 3 cubed, and 10 to the minus 6 times 10 to the minus 6 times 10 to the minus 6, so 10 to the minus 18 cubic meters. Now, we can do this exactly, but it's also fine, and it'll work out perfectly well on the homework if you'd want to just do this a little bit approximately, and say pi is roughly 3, and then this becomes 4 times 3 cubed, which is 27, times 10 to the minus 18 cubic meters. And to also be a bit approximate, 4 times 27, it's kind of like 4 times 25, so we're going to call that 100, times 10 to the minus 18 cubic meters. So now our volume fraction is then the volume of our DNA, 8 times 10 to the minus 18 cubic meters, divided by the volume of our nucleus, 100 times 10 to the minus 18 cubic meters. Again, this part cancels out, and we're just left with 8 over 100, which is 8%. Pretty neat. Okay, so one thing, don't forget that on Canvas what I'm asking for is the percentage. So here, I mean, this is just an example, but if you were to enter this, you would enter the number 8. The number 8 for 8%. So then in the actual problems, the first one is very similar to the one we just did. So in number 14, most of this is exactly the same, except the DNA part is a little different. We only have one copy of the genome instead of two. So we have half the DNA volume that we did in the previous thing before. And then for the sperm cell, the sphere is a sphere of radius 2 microns rather than 3. It's a smaller space. And you'll get a percentage. I'll give you a hint that it shouldn't be wildly different from what you figured out in the example before. And then the other two, the length, so for number 15, we have a different length of DNA. So we have a little bacterium swimming around there, and it's got DNA inside of it in a little kind of region here that has a radius of 0.25 microns. And the length of the DNA is different as well. It's 5,000-ish base pairs. It's in that table there, so the length of DNA is different. Okay, and then in number 16, look at a virus. Good, so think through this, and hopefully this helped you out. And yeah, good luck, and be careful with your powers of 10.